So Ruben Wiersma is a senior PhD student, and we should post the collaboration as well. Yeah, and we'll talk about some geometric component perspective there.
Yeah, thanks for having me in this talk, and thanks Klaus for introducing geometric deep learning and on surface elements, because that's what we'll build on. So we found before this problem of having coordinate systems or having no global coordinate systems, we wanted to use local coordinate systems. And we've seen before some of these examples, graph-based approaches ignore directions, what Klaus just mentioned, going volumetric, so using 3D extrinsic kernels, and then these final ones with the matching are filtered kernels to the surface. And in harmonic surface networks, we show that you can use these rotation invariant, rotation aggregate kernels, apply them in different directions, and we have filters that we can rotate after. So that is everything that Klaus just explained with harmonic surface networks. Also, shown before is these limitations that you require this good exponential map. So we have this, we need this parameterization, a local parameterization to apply our filters. And that can be quite expensive to compute and sometimes quite tricky for different discretizations of our geometry. The second is that circular harmonics can be quite complicated and sometimes expensive to evaluate. So the question was, how can we move further? How can we simplify this and still have all these benefits? And that is where DeltaConv comes in and this presentation starts. Now, the idea that we start with is rather than looking as a charting-based approach where we think of this filter moving over the surface, we consider operators as ways of formulating convolution. And operators are familiar to you if you've done some geometric deep learning before. An example of using operators in geometric deep learning is the Laplacian. And when you've used GCN, you've used the graph Laplacian, which is often formulated not as this operator approach, but as this aggregation of the weighting of your neighbors. But this encodes the graph Laplacian, which is a way of formulating convolution in the set. Another place where this has been used is in diffusion net, where they use not just the graph Laplacian, but a geometric Laplacian. So there's also encodes geometric information. And this has been used before. Now, a benefit of doing this is that the networks that use these operators are coordinate independent. So the operators themselves deal with all the coordinate systems and whatever discretization you have, but the network that uses these operators doesn't need to consider these coordinates. But a downside of only using the Laplacian is that it is isotropic, so it doesn't encode directional information. And with DeltaConv, we try to look at how can you introduce anisotropy, so having directional information inside your network, by still using these operators. And we use a way of making this Laplacian anisotropic that is based on a lot of very classic ideas. And it works as follows. So the way that you can make a Laplacian anisotropic is by breaking it up into its separate components. So I'll explain a bit more what a Laplacian is, but it's the second derivative operator. So you can break it up into gradient and divergence. So it's twice the derivative. And to make it anisotropic, you can apply nonlinearity in between. So that's the strategy that we'll apply. To introduce these operators a bit, so Klaus mentioned before that in differential geometry, we study the derivatives of our mappings. And these are these derivatives. So Laplacian is the sum of second derivatives. In the discrete setting, so when you're discretizing a mesh, for example, you can think of it as the difference to the average of your neighbors. And this Laplacian is used in many applications. So solving commodity functions, solving the heat equation, spectral analysis, and the applications that Klaus also showed, and a downside is isotropic. Next, the gradient operator. This is an operator that, if you apply it to a function, the output represents the largest rate of change of this function and the direction. We often represent it as vectors, as a vector field. We also use the cogradient, which is a 90-degree rotated version of this vector. On the surface, these gradient vectors are tangential. So we don't need any 3D or coordinates that go away from the surface because the signal doesn't change away from the surface. So it will always only change in tangential direction. Divergence and curl are operators that we apply to vector fields. Divergence measures sinks and sources. So here, for example, there is the source of this vector field. And curl measures vortices. So a visual picture or mental image you can have with this is like a stick in the water that's rotating in a vortex. It measures where this vector field rotates around points. If we want to discretize these operators for meshes, there's a whole way to do this. In this paper, we look at discretizing them on point clouds. And what we do there is we use a moving least squares approach. So the idea is that we fit a small patch, for every small patch of surface, we fit a quadratic polynomial, and then we compute the derivatives of this quadratic polynomial. And that gives us the gradient and divergence. For point clouds, you need to take care that this fitting is done well, so you need to regularize, because otherwise you get really bad gradients that explode. So that's something you have to take care of, and we describe in this paper. So back to this picture of gradient, divergence, breaking that up with a nonlinearity. How do we transfer this to a neural network that we can learn anisotropic information? So the idea is that we start with a similar two-stream approach that we saw before with harmonic surface networks. And rather than encoding them with rotation invariance or rotation equivariance, we just call them scalars and vectors. And as we saw before, gradient maps from a scalar function to a vector field. Divergence maps back from vector functions to scalars. So that's how we move between these streams of information. If we want to make this into a neural network, then we have scalar features, for example, for every point on the point cloud, vector features for every point in this vector tree. And when I say vector feature, I mean, so these are these 2D vectors in the tangent plane. We can encode them in any way we like. We choose to encode them as vectors in this tangent plane by 2 coordinates. And because these operators are coordinate independent, we can use any rotation of the coordinate system. The operators take care of this. All right, so how do we actually learn features from this? So how can a network find out that there's this wing somewhere or there's the front somewhere? Well, the first ability we give to the network is to just learn per point features using multi-layer perceptron. This you might be familiar with if you've used Wind, for example. On scalar features, this is straightforward, multi-layer perceptron. And on vector features, we mirror this approach. So a multi-layer perceptron always is a weighted sum of your features and then the nonlinearity. For vectors, it's a weighted sum of your vectors and then nonlinearity based on vector norms. Now, because we take a weighted sum of vectors as a whole, this is also coordinate independent. Then we make these connections between the streams, so gradient, divergence, we concatenate them, and then these multi-layer perceptron after it allows the network to combine these operators. In our final version, we try to find the best of both worlds between what pointnet is, so we do use its maximum approach, and we showed that some ablation sense of why we do this. Now let's go back to the properties that we wanted. So we wanted some form of anisotropic. So if you're familiar with anisotropic diffusion, this is a good example of showing that DeltaConv can approach this type of anisotropy by showing that it can approximate anisotropic diffusion. Now, what is anisotropic diffusion? It's so you're diffusing a signal over time. So it's this process where it's like blurring information. So it's like diffusing heat. And it happens only in certain directions. So it's anisotropic. So it's not in every direction the same way that it diffuses, but it diffuses in certain directions more, in other directions less. This process can be described by a differential equation. So you say the function changes over time, and this change of time is computed by the gradient of this function, multiplied with a nonlinearity applied to the function, and then divergence. You can solve this equation by swiftly integrating over time, and if you do that for a couple of steps, you see that it diffuses information in certain directions and in other directions not. Now, this specific implementation of anisotropic diffusion diffuses along or doesn't diffuse over edges. So that's the specific filter that was used here. In DeltaConv, we have the same building blocks that can do this. So we have gradients and nonlinearity and divergence. but the function here isn't fixed. That is something that the network can learn. So it has this ability, for example, maybe if you're familiar with GCN, there's this idea of diffusion as a way to learn features. Here we add the ability to learn anisotropic diffusion as a way to learn anisotropic features. We can show with a very simple experiment this difference between the property that DeltaConv can do this and other networks can't by overfitting on this image. So the input is this image, the output is anisotropic diffusion, and with a network that has fewer layers than the number of time steps, we can approximate this diffusion. That's not the case for other types of graph-based approaches that are either isotropic. So this is a very good example. GCN is, we know, is isotropic, so it only has isotropic diffusion. But also other types that might have some form of anisotropy, like DeltaConv, are not able to do this well. And as I said, we can also approach for diffusion times. So if we overfit on several types of sets, also we can approximate. Now another property, so aside from this anisotropic property, we can also benefit from a lot of properties with geometric operators. So they're all intrinsic, which is important if you want to have moving shapes. They're also coordinate independent, so that's solved for us. All these operators are generalizable to other types of surfaces, and there's a lot of work already studied on how to make these operators for different discretizations, so we can simply make use of that information and learnings and incorporate that. In our experiments, we tested on point cloud tasks because they were very widely available data for classification, segmentation, also classification on scanned data sets. And in the paper, we compared to, at that time, state-of-the-art approaches. And we showed that with a simple network, so often these state-of-the-art approaches use UNets, multi-hierarchies. We just use a couple of layers, no hierarchy, and we can still match the state-of-the-art, sometimes improve on it. What we find really interesting is to see if this directional information actually adds to the performance. That's what this experiment does. So what we start with is a network where we only learn scalar features that is using this geometric Laplace operator, the graph Laplace operator, and this maximum aggregation that we see in point plus plus and DeltaConv. And the first step we do is just to increase the number of features in the scalar sheet. Sometimes complexity already helps in improving accuracy. We see here that it doesn't do too much. Instead of increasing complexity, just increasing the number of features, we add the vector screen, and then we see there's improvement in the vectors. So that to us shows that this anisotropy, these vector features really add to these tasks. Another ablation we do is to look at speed, and there we see that representing directional information on points actually helps with speed versus representing values that's done. So the conclusion is that we can create intrinsic anisotropic convolutions are challenging on surfaces. With DeltaConv, we combine and compose geometric operators to create these anisotropic operators that are both intrinsic and anisotropic. And we also show in the paper and in our code that it's pretty easy to use and also efficient. And if you want to find out more, you can find out the GitHub or use the build package to use them. And you can always contact us at the graphics group. We're always happy to help and collaborate. So that's it. Thank you for your attention.